Okay, so again, for the umpteenth millionth time. So you've got analysis of variance, you've got more than two groups. If you have two groups, you know which is what, you know what's what, you know what group differs from what. If you have more than two groups, the question then is, now, so you know the HO is mu1 equals mu2 equals mu3 equals ... mu k. In the assignment's case, equals mu4. That's the null. But the alternative doesn't say mu1 is not equal to mu2. Which means differ from which means? It doesn't. Analysis of variance does not answer that question. It says our two means different. It doesn't say which two means are different. Yeah, sometimes you might say, I don't care, it's done. I have 3 control groups and an experimental group. I can look at the graph and the 3 control groups are down here, the experimental group's up here. If anybody tells you you have to go any further than that, punch them and say it's for me. You don't have to. But usually that's not the case. Usually you have more than, let's say you got 3 groups, 4 groups, and you don't know which is which is different. So one of the things you can do is you can do t-tests. So after you've done analysis of variance, then do a whole bunch of t-tests in essence. The problem is the alpha level goes up. The alpha level goes up. Because if you use 0.05 as your alpha level, suddenly now, let's say you got 3 t-tests in, and suddenly your alpha level's gone up from 0.05. It's not 0.05 anymore. If let's say you had 20, let's say you had like 7 or 8 groups, then you're hitting like 20 t-tests, chances are you're going to find one by random chance alone at 0.05, right? Uh-oh. So it's called the Bonferroni correction, which sounds a lot like beefaroni, so it's delicious. The Bonferroni procedure takes care of this. What it does is it takes 1 over n. 1 over n is the number of comparisons. Okay? Number of comparisons you're going to run. So let's say you're going to do 5 t-tests. It's 1 over 5 times alpha. Now alpha is 0.05. So now you end up with 0.01. Okay? That's one approach to do it. And that's a pretty common one. And there's nothing wrong with it. The t-test really just looks a little bit different. It's called t prime. And it's x bar 1 minus x bar 2. So that's the first one you're comparing and the second one, whatever. And it's divided by the square root of 2 times the mean squared error over the number of subjects per group. Note that means the number of subjects per group should be equal. And you should try to do that anyway. You should always try to do that. So what is that? What? Wait, think about a t-test. Think about a t-test, guys. 2 sample t-test. Bar 1 minus x bar 2 all over the square root of that. Just variances. Well, we have a variance estimate. Mean squared error, we've calculated it. And look, we're adding it up so we get 2 of them. 2 mean squared error. That's all. Nothing magic. Okay. Very simple. By the way, you wouldn't do this by hand. Once you've done the ANOVA on, say, SPSS, just check the little checkbox, and it says post-hocs, or it might say comparisons, and I'm not sure which, and it can just do it. What I typically have done, though, in my career, when I've ever done one of these post-hoc tests, this is also pretty easy to do. I have the mean squared error in front of me. I can, rather than run it again and click a box, this takes 30 seconds. It's not hard to do, right? So that's one approach. Do you see why this is sensible? Pretty simple, right? Now I know what group differs from what group. What the Bonferroni has done is it has lowered the alpha level. Here's another way to do it. There's lots of ways. It's called the studentized range. You calculate something called the Q statistic. I don't know why it's called the Q statistic. That's what they call it. I'm never going to ask these formulas because they're really just all t-tests. I mean, they really are. This is all, look, it's almost the same except we don't have 2 mean squared error, we just have 1 mean squared error. That's all, it's the only difference. And the corresponding test statistic is a t-like statistic, except it's changed a little bit such that the critical values have changed a little bit. Let's just leave it at that. Okay. You could do this what's called the student Newman Keuls test. Wait, what is this? Okay, look up in a table. This is how hard this is. Look up in a table the critical value for Q with R comparisons. You're going to do R comparisons. So let's say you got 5 comparisons. You look up 5. And then with 0.05, and the degrees of freedom is the number of subjects minus 1. So you got that. You multiply that number that you look up in a table times the square root of the mean squared error over n. You get this value called W. So now, if any two, let's say you calculate this and the W ends up being 6. That means any two means that are different by 6 are significantly different. That's all it is. Again, no one does these by hand. This is one of the few slides that I have to look them over each before I give this lecture, because I don't know these formulas off by heart. Why should I? Right? That's all it does. So 6. Okay, this means 18 and this means 12. Oh, that's too bad. Sorry. 11 and a half. Let's make it 11 and a half so they're clearly different by more than 6. You look at that and go, oh, those two are different. Done. They are significantly different. That's called a student Newman Keuls or a student Newman Keuls. Okay. There's another version of this called Tukey's HSD. HSD stands for honestly significantly different. It's a great title. And all it does is just uses the largest possible range. Just says, okay, there's 4 means. How many possible 4 groups? How many comparisons are there? 6. I think it's 6. If there's 6 possible comparisons, so just make it big as possible. And this is a very liberal kind of test. Very liberal kind of test. Very commonly used one. Okay. So there's Tukey's, Newman Keuls, Studentized range, that's where that comes from. That distribution. Oh, there's also one called the Scheffé test. That is so conservative that it often says you have no significant differences even though your analysis of variance is significant, which tells me that I don't want to ever use that test. It's called Scheffé's LSD, least significant difference. No one uses it. You never see someone in a paper saying, then I did Scheffé test. So why would you do that? You already found a significant effect, and then it's like, it might not even show up. So most people probably go with, well, first of all, most people just do all of them and then find the one that fits their hypothesis. You shouldn't really do that. That's what most people probably do. I would stick to the same one with the paper. As a practical piece of advice, I wouldn't say, you know what I'll do? I'll just, well, in this experiment, and in the next one I changed. And don't explain why you changed. Don't do that. In fact, an editor, or if it's a thesis paper, your advisor will go, you can't do that. It's not like you can just change what weapon you're using in the middle of a fight, like it's Assassin's Creed or something. You can't do that.
Well, if you have print draw.
Well, that doesn't matter. Can't do that. Just don't do it. Especially the newer ones, because you can't pause and change. You have to do it on the fly. It's hard. So I'd stick to one in the paper. I've usually used HSD. It's the one that it's pretty liberal, but it's not too liberal. So that's the one I've gone with. All right. Questions on that? Does that make sense, what we've done here? All you've done is you've determined which two means are different. You've got a pack, because all analysis of variance is that 2 of the means are different. I don't know which 2 they are. There is a school of thought that I have some sympathy with, which is, why are you using analysis of variance if you care about just one mean being different from another set of means? Why not just do a t-test in the first place? And I have some sympathy for that argument. I've often said to people, students will say to me, well, I want to do post-hoc comparisons now. And I'll say, why? Look, we're interested in the pattern in your data. Look, the pattern in your data shows that exactly what we expected. Why not just stop now? There's no reason to make it more complicated. But mine, by the way, is a minority view. I'll say that, just to be clear about that. All right, questions about that? That's pretty straightforward, right? No problem.